Okay. So last time we talked a little bit about absolute value functions, right? Because we're starting chapter 2 about absolute value functions. And we were talking about simplifying, right? And basically we have made like a do's list and a don'ts list. The do's lists are like things that we can do all the time, and the don'ts are the things that don't work all the time, right? Is this sounding familiar? Okay. So things that were in the do's list. We had this one. Let's see, what wasn't in, or what was in the don'ts list? We had this. Similarly, we had this. Trying to remember what else we did. Let me just go back and cheat. All right, if you don't have a good memory. Okay, there's just those three. Okay. And then I guess we'll, I don't know why I started at 2 there. You know, whatever. You start at whatever number you want, right? You're Mr. Kulik. You're teaching the class. You can number things wherever you want. And I guess we did this silly one too, that we said that that doesn't work either. Was okay? Okay, so this is just kind of recapping the things that we saw last time. Let's add a couple in here. So if multiplication works, division should also work, right? Because we can just think about multiplying by a reciprocal is the same thing as division. Something else that doesn't. And this is another one that's very common mistake for students to make, is that we can't distribute into a absolute value. Where's that going to get us into trouble? Okay, so specifically, like, what value of A would cause those two things not to be equal? What kind of value of A? If A is positive, those two sides are equal, right? If A is 0, those two sides would be equal. But if A is negative, the left-hand side would be negative, but the right-hand side has got to be positive, right? Can we see that? So that's very easy to make that mistake because the absolute value looks so much like a parenthesis. It's easy to want to just distribute things inside of there. Please don't do that. Okay? How many of these are things that you guys had already kind of known before intuitively, and how many of these are like things that are like, maybe I never thought of it, but I guess this makes sense? We're doing this because these are things that I see students every year do. So this is just me trying to kind of head some of these off before they become like learned patterns that you have, so we can kind of undo that before we get going. Did you have something that you're going to ask? No? Okay. So let's do a couple of just numeric examples here to just kind of those are the obvious ones that have popped up in my mind. If we come across some other ones that people are trying to use later, we can always circle back and kind of talk about those too. So if I want to simplify the absolute value of negative 3x, I can use that first of my do's to rewrite this as the absolute value of negative 3 times the absolute value of x. And the absolute value of negative 3 we can just write as 3, right? Can I do anything with the absolute value of x? No. That has to stay just the way it is, right? Everybody's okay there? What about negative 5 times the absolute value of x plus 4? What would I do here? Yes, sir. Perfect. Thank you. Excellent. So there was nothing to do here, right? You can't distribute in the negative 5. You can't break the absolute value at the addition symbol. There is nothing for us to do here. That's as simple as that one could get. You ready for some sneaky stuff? Oops. Need the end to the absolute value. Okay, any ideas? When you see something that looks like x squared plus 2x plus 1, what do you think? Do you recognize that type of expression? It's called a, starts with a Q, quadratic. Okay. What are, when you dealt with quadratics before, what is something we can do to quadratics? Factor, right? Does anybody see how we would factor this one? It's okay if we're a little fuzzy on this. That's okay. We're going to talk about quadratics and factoring again this year. So if you don't remember all of that right now, that's okay. Just to be clear. Yes. Okay. And it's Amy, Sydney. I was not even close. I should have the attendance sheet opened up so I can try to cheat again. But that's very good. So the trick is that when the leading coefficient is 1, like it is here, I just need to find the two numbers that multiply to give me 1 and add to give me 2. Those numbers are 1 and 1, which tell you kind of how to factor this. We'll do like a whole chapter talking about quadratics and review this type of factoring technique and the more general version of it in a great deal of detail later on this semester. So if you are like, this is all news to me, that's okay. We'll do it again in a couple weeks really well. So if you don't know how to do that already, you will later on, and I don't expect you to know how to do it now. I was hoping that somebody would remember how to do it. Okay. So that's good. What can we do with this? This is sure. That's fine. And what can I do with that? Yes. I mean, you can, but that's not really getting us anywhere forward. That's not to say that's not true. And there may be cases where like putting a 1 somewhere like that is a useful step, right? When we multiply fractions or when we make common denominators, that's essentially what we're doing. Here, though, it's not really what I'm driving for, and it's not what we want to move to a more simplified form. What's x times x? X squared. So what's the absolute value of x plus 1 times the absolute value of x plus 1? About it's the absolute value of x plus 1 squared, right? Because we have 2 of those things being multiplied together. Everybody's okay with that idea? And what can we say about the sign of something squared? It's always positive, right? So what can I do? I can drop the absolute value symbol because the squared already guarantees that it's positive. So let's go back up to our do's list and let's add that one in because, well, I didn't think of it initially. We can just add that. So regardless of where that squared is, it allows us to drop the absolute value. Is everybody okay there? And really, does it have to be a squared? If it's an even number, that'll do, right? If it's a 4 or 6 or 8, any even exponent will allow us to do that. The one thing to kind of keep in mind, if we have like x squared plus y squared, you can't just make that x squared plus y squared. I shouldn't say that, because that is true. What do I want to say here? Let's make this like plus a constant. Actually, let's not. I'm not even going to get into that. All right, sorry. I apologize. I take that back. Everybody's okay still? Sorry for being messy and just kind of exploring here, but it's fun to do some little exploring, right? Find out if we can come up with a rule or something. Do some sneaky stuff. Show you some sneaky things. Okay. So the main point here with the simplifying, there's not much I would expect you to be able to do with this, specifically simplifying on a test or a quiz or something, right? Because there's not a whole lot of complexity we can ask you to do here. Mainly what I want to do with the simplifying is go through some of these rules. So when we do some solving or deal with some graphing things where we have to like do some numeric simplification, we know what we can and can't do with an absolute value because it makes a big difference. Okay? Let's move to solving. So we have let's say we have an absolute value equation. And we want to think about what are the possible types of solution sets that we could get from an absolute value equation. So let's just say like we have the absolute value of x equal to some constant a. So a is not another variable, it's a constant. We just haven't specified exactly which constant it is. Okay? So to solve this equation, how many different types of solution sets might we get? Can we get exactly, you say, okay, Sydney, tell me what you're thinking. Because you have an idea, and I love that you want to participate, and I want to hear what you got. So you say 2 answers. Okay. Can you give me an example of when we would have 2 answers? Perfect. Everybody's okay with that? Can we generalize this? Instead of being a specifically the number 4, if a is any positive number, right? You're going to get 2 answers. Okay? Is it possible for something else to happen? Okay. Mayo? I'm in the wrong hour or something. Natalie. I'm sorry. So if A is negative and then you between the mask and a little bit of trail off.
I don't know what I'm saying.
Okay. No, that's okay. No, I think you have good ideas. I think you're thinking about this exactly the right way. Right? We've got A can be positive. So what happens when A is negative? Perfectly reasonable thing to say. What is going to happen when A is negative? No solution, right? The absolute value can't give you a negative answer. So you can have no solution when A is negative. Okay? Have we covered all the possibilities? There's one more, right? What's the last possibility? When A is 0, how many answers are we going to get there? Just 1. So, when solving an absolute value equation, we have lots of possible things that can happen, right? We have 1 solution. We can have 2 solutions. We can have no solutions. And at times, depending on the construction of the equation, it's not going to be obvious just from looking at it which situation we're going to be in. And in fact, there's going to be instances where we solve and we get 2 answers and not both of them work. Or either of them work. So we're going to have to be careful here. So let's define that situation. An extraneous solution is an apparent algebraic solution to an equation that does not actually satisfy the equation. So it's going to be a situation where we follow our normal solving algorithm, the one that we'll develop here in a few minutes, and we get a result or two results, but if we go back and check them, they may or may not work. If they do not work, that's what we're calling an extraneous solution. Now, a very trivial example here. Actually, let's wait till we outline the solving algorithm. Why would I show you an example of an extraneous solution if we haven't showed you how to solve it yet? That seems backwards, right? So we'll come back to an example of this in a moment. Okay. So solving. So we're going to follow the reverse order of operations, except I'm going to, instead of calling this an exponent, I'm going to call it O for operation. And this is where the absolute value is going to live. So when we're solving, we're going to be working from the right to the left on our order of operations. When we simplify, we go the other direction. Just to be clear. Yes, Sydney. Of course. So far, so good. We haven't really done much yet, but I like checking in. Okay. So let's just look at an example. Let's say we have -3 times the absolute value of x plus 5 minus 7 equals -10. What would you think the first thing we should do to solve this is? Mia? Add 7 to both sides, right? So the first thing we want to do is order of operation is undo any addition or subtraction. Well, I see subtraction here with the -7 and addition here with the -5. However, that -5 is like inside the operation, so we have to wait until we've cleared the operation before we can undo that +5. Does that make sense to everybody? And then what should we do next? Is it Ella? I'm like 1 for 25 today. Perfect. Yes. Okay. Now that leaves us with the absolute value. How do we undo an absolute value? Just make a little aside here. We'll talk about this. So remember when we defined defined the absolute value? And one of our definitions was this piecewise definition. That's what we're going to use to generate our absolute value, or to eliminate the absolute value. So we have to split this into two pieces. We're going to split this into two equations. The first equation, the answer is positive, so I'm going to have just the stuff on the absolute value is going to equal the positive. In the second equation, the answer is going to be negative. So I'm going to have just the stuff in the parentheses, but the negation of the right-hand side. Is everybody okay there? Okay. And now we'll just continue solving this, or each of these two equations separately. So for x plus 5 equals 1, well, that's really easy, right? So one answer is negative 4. And the other answer is negative 6. Is everybody okay there? Do we know that both of these answers are okay? We should check, because we just a moment ago established that it's possible to get like these extraneous solutions. Things that that's an answer we get doing this algebraic process that might not actually satisfy the actual equation that we're working with. So let's check negative 4 first. So I go back to the original equation, and I'm just going to plug negative 4 in for x. Right, that's what I had, I think. So if we do this, working from the order of operations here, I'm going to add the stuff in the inside. So negative 4 plus 5 is 1. Absolute value of 1 is just 1. Negative 3 times 1 is negative 3. And negative 10 is equal to negative 10. So we know that x equals 4 is a solution. Is everybody okay there? Then we should also check x equals negative 6. So if we do the same thing, and we kind of yada yada yada, you're going to get the same result. So we have two solutions to this. Okay? So I skipped some steps here, but I assume you can take my word for it, right? If you look at it for a second, you'll be like, oh yeah, the absolute value of negative 6 plus 5 is just going to be 1. And then it's essentially here. And you're good to go. Okay. So we've seen an instance where we get two solutions, right? In general, if my equation has x in one place, notice here that I have x in just one location, I'm never going to get an extraneous solution. Unless you do something silly, like miss that you have an absolute value equal to a negative at some point. So let me just illustrate the only situation where you can get an extraneous solution, but I would contend that like common sense would stop you before you got to that point. But sometimes common sense goes out the window when we're stressed, so like we should certainly talk about that situation. Okay? So let's say we have this. First step, what would I do here? Very good. Then what? Divide by -2. And then what? Yeah, at this point you could stop, right? How do we know that there's no solution here without having to finish solving this? If I look at the left-hand side, I have an absolute value. That's it, right? On the right-hand side, I have a negative. Can an absolute value ever give me a negative? So you could stop right here and say no solution. Now, in the midst of a high-stress situation, you might miss that. It's conceivable, right? If we're just used to doing some solving, and that doesn't happen very often, where we get absolute value equal to a negative, it's perfectly plausible that you're going on a test or something and like just blow right past this, right? You can see yourself doing that. It's not unreasonable. So let's see what would end up happening here. So I'll split my absolute value into two pieces. The first piece does nothing, and the second piece we negate the right-hand side. So when I solve this, I get -13/3. And when I solve this one, I get 1. I skipped some solving steps there. I hope that's okay with everybody. I trust that we can piece together some of that stuff in our head, right? Or if you needed to, you could certainly write down and fill in those intermediate steps if you like. Is that okay? This is why the check is important. So when we check, we have to make sure we're checking all the way back at the beginning. I forget even 3x plus 5. Okay. And it was -6. So if we do this, oops, 3 times -13/3 is just -13. And -13 plus 5 is -8. And the absolute value of 8 is, sorry, the absolute value of -8 is, oh my goodness, guys, it's -2 out front. You let me get too far with making a mistake. -2 is the out front, excuse me. So that's going to give me -16. And I get -22, which is definitely not equal to 10. Whoa! I was like, wait a minute, this is starting to check. What's the matter here? What did I miscopy? So that doesn't work. Similarly, x equals 1 is not going to work. If you discard both of the solutions, the result is no solution then. Okay. So, again, this is the only way you're going to get extraneous solutions when the x is in one place in the problem. So what do I mean by one place? I mean that, like, I have just one x in my equation. There's not a second x somewhere else. Let's look at a situation where we do have an x somewhere else. Okay? Sound good to you guys? So far we're okay? Clear what we're doing? Okay. I'm just checking in. You know? I don't want to be going too fast or leaving anybody behind. So let's say we have let's say we have this. Okay. So here, what would we want to do first? Yes. Jane? That's 2 in a row, guys. Yes, I agree. So in general, what we're trying to do here is to isolate the absolute value part, because we got to get that absolute value part by itself in order to get rid of it. We can't break it into 2 equations if there's still other stuff with the absolute value. So we have to get that thing by itself. And now I've kind of given away what to do next, right? Which would be to split this into 2 equations to get rid of the absolute value. So the first equation, I don't do anything other than get rid of the absolute value. In the second equation, we need to make sure we negate the right-hand side. So you notice that even before this, when there was just a single number, I put a negative and a parenthesis around the whole thing. And you might have thought that was kind of a silly waste of notation. I'm doing it specifically for this situation, so I'm used to doing that. So I don't just stick the negative sign in front of the 2x. Because what do we have to do when I have a negative out front of a, like an expression like this that contains more than one term? Yeah, I have to make sure I distribute that negative, right? That is the number 1 mistake that students in this class make when solving absolute value equations, is forgetting to distribute negatives. It's a very easy mistake to make. That's why I'm pointing it out to you right now and kind of making a big deal about it. And I'm trying my best in the notation that I'm using to kind of track through the work along the way, to do it in a way that it makes it hard to forget to do that. Okay. We can solve each one of these 2 separately. So I'm going to move the x's onto one side and the numbers onto the other. So I have x equals -4. And I have 16 is equal to -3x. Or -16/3 is equal to x. Is everybody okay there? Again, I did 2 steps in 1 line of work there, right? But I tried to do it in such a way that hopefully it was clear. So here, it is critically important that we're checking. Here, there's no good predictor of whether we're going to get an extraneous solution or not. And I'm going to go back and look at the original problem again so I don't make a mistake like I did the previous time. Okay. That's it, right? Just plus 2x plus. Okay. Now I have it. Except I want to write -4 there where I wrote x, right? Okay. Goodness gracious, Mr. Kulik. Quit making me erase all these things. Well, that's what you get for trying to write this stuff down before I've gone back and double and triple check myself so that I can copy something down correctly from 5 minutes ago. It's harder than it looks. Okay, so we'll just start simplifying. So I'll do the stuff inside the absolute value, and I'll do that multiplication. So that one worked. Let's check the other one. This one's going to be a little irritating because we have these fractions rolling around, but we'll just have to put on our big boy and girl pants to deal with it. But we learned how to deal with fractions at some point. We may not remember how to deal with them, but we did remember, or we did do it at one point. And allegedly we're pretty proficient at it. So I'll make a common denominator. And to do the multiplication, I don't need any common denominator. So add those fractions. And we'll make another common denominator. And then make a common denominator. We'll add those fractions. And we got that this one doesn't work. So we have just one solution to this problem. Just x equals -4. This one is extraneous. Is that okay with you guys? And they really don't get considerably more, like, maybe I should say, appreciably more complicated than this. In this particular example, the solving ones that you guys will encounter. They're not too bad. Let's take one moment. Actually, let's put this on the table for to come back later. I want to do this a little bit later. But this is an important question. Like, what did we do in here that generates the possibility of getting extraneous solutions? This hasn't happened ever before in algebra, right? We've solved lots of things and never had to worry about these extraneous solutions. So think on that for a minute. We'll circle back to it a little bit later in this chapter. But it is a question I want to address, and if I forget to come back and address it, please somebody remind me, because it's I think really interesting. Okay? But we're not quite ready to talk. I'm not quite ready to talk about it yet. There's some more things that I want to talk about in this chapter before I circle back to that. Okay, so we've done solving absolute value equations. You guys feel reasonably comfortable that you could do problems in that same vein of those things that we've done in examples? Okay. Let's do then absolute value, or solving absolute value inequalities. Okay. So back in your Algebra 1 class, you solved inequalities, or you likely solved inequalities, at least in some past pre-algebra or algebra class, right? Remember doing something like this where you had like x plus 7 is less than 10? Okay. What was the one tricky thing you had to remember when you're solving an inequality? Neil? Yes. So it's actually multiplying or dividing by a negative, flips the direction of the inequality. So need to remember that. Again, that's easy to forget, which is why I'm making a point and taking a moment and asking us to kind of remember that. Easy to forget to do that. Okay. Okay. So let's say we have this inequality. We'll start the same way we would as solving an equality. So what should I do first? Subtract 6. Very good. Okay. And then what would you like to do? Ella? I agree. Divide by -3. When we do that, though, what do we have to remember? Yeah. So that's going to become greater than. Okay. And now what do? We split it into 2. Very good. So the first split, nothing changes. The second split, we negate the right-hand side, and this inequality symbol changes direction. So when you break it into 2, the inequality that you negate, you also have to remember to flip the direction of that inequality symbol. That happens every time. So any absolute value inequality you solve, at some point you're going to flip that inequality symbol. Even if everything was positive along the way, when you do the split, every time you do the split, you have to remember to make that flip. But only for the side that you negate. Okay? And then from here we can continue on. So subtract 5 from both sides. Oops. Okay, and then we'll divide by -2. What do we have to remember there, though? Yeah. This is sign flipperoonie here, flipapalooza. So we have these 2 inequalities. Yes, Sydney. I forgot to, after I made a big deal of it. Thank you. You ever make a mistake? Happened to me. That's it. I'm making jokes. Anyways, I thought that was going to be funnier than it was. Nobody laughed, though. Goodness gracious. All right. So there is one other thing that we need for our answer. We don't know whether this is an and inequality or an or inequality. The easiest way to tell that is to graph both of these inequalities on the same number line. So there is x is less than negative a half. And here is x is greater than 11 over 2. When both the arrows are pointing away from each other like that, that's an OR inequality. So we'd say our final answer is that. If both the arrows point towards each other, it's and. If they're both pointing the same direction, you made a mistake. The likely mistake that you made is when you split into two inequalities, you forgot to flip the sign. Or you did a Mr. Kulik a few seconds ago and talked about flipping the sign, and then you forgot to do it. Okay? Let's do one more, and that should be that, right? This is not terribly different than the solving, correct? Let's do one more. Oh, excuse me. Oh, excuse me. Do I want that? Let's do that. Okay. I'm sorry, hold on. I want this to turn out a certain way. Okay, I didn't want it to be that. My apologies. Okay, so we got this guy. What do I want to do first? Subtract the 6. Very good. And then what? 5 by 3. Okay, and then what? Split. What should the first inequality be? Okay, and the second one should be? Very good. And then we can just solve each of these separately. Notice here that I'm not flipping the inequality because I'm not multiplying or dividing by -7. I'm just subtracting, which is perfectly fine. So x is less than -10, and I still didn't do this to what I wanted it to. And greater than -4, so this one should be a OR. That's frustrating. You ever think hard about something and you're like, this is right, and then you get down to the end and you're like, I should have done it the other way. Great googly moogly. Okay, so what did I have? I had this And I had like plus, or I had minus 6 is equal to 9 or something at the end. 15 plus 6 equals 15. Okay, and we did greater than. So suppose it was less than. What's the only thing that's going to change? Yeah, so I should have this, and I should have that, right? Everybody agree?
Do you like always flip the sign, like no matter what you divide, or is it like negative or positive?
Only when it's in dividing by a negative or multiplying by a negative is the only time you're doing it. This is just a separate example, so I shortcutted through all the algebra because I want to just show you what the and looks like. And I was too dumb in trying to do it the other way to plan ahead to get it to work, which is really kind of embarrassing for me, but you know what? That's life. Okay, so that's this one. So when I write the and, there's two different ways I could write it. I can write it this way. Alternatively, I could write it, this way. And either of those answers is appropriate. Mia?
Let's say it was like x is less than negative 1, and x is greater than negative 10. Would it be almost every and since negative 14 is not for them on the graph?
Yes. So even if this was like strictly less than and greater than, it's still an and. All we're caring about for the and is like, do the arrows point towards each other and arrows pointing away, or whether they're filled in dots because it's an or equal to, or if they were empty circles because it was a strict inequality, doesn't affect the and or or. So that's a good question. And also brings up pointing out that like whether we filled in the dots on the number line mattered, right? You guys remember that from your algebra, pre-algebra course? Okay. What do we have? Still lots of time still, huh? Okay. What do we want to talk about next? Well, I guess let's start talking about graphing. So, from last chapter, we said that g of x is equal to so we can view any transformation of f of x as this function g of x, right? Where our parent function is this y equals f of x, which should be the simplest version of the function we're talking about. So for absolute values, what do you think our f of x is going to look like? What's the simplest absolute value equation you could write? The absolute value of x. Everybody okay there? Or you haven't multiplied by anything or divided by anything or added by anything or subtracted by anything. It's like the simplest thing you could do that involves an absolute value and a variable. Everybody okay there? So that means that any absolute value function then can be written in this form. Okay there? Now take a look at that for a moment. Notice that we have multiplication going on inside the absolute value, right? There's really some multiplication going on right here. Could we simplify this? We could, right? Everybody's okay there? And 1 over b is just a constant, right? Like these a, b, h, and k's are just constants. They're not actually variables. Now they're representing like an arbitrary constant where we haven't told you what it is. But it's not like it's the variable, like the independent or dependent variable when we go to graph something, right? So the absolute value of b is just, or I'm sorry, the absolute value of 1 over b is just 1 over b. So what does this say here then? Notice that we could take this 1 over b factor and combine it with the a that's out front, right? This tells us that every horizontal stretch or shrink can be thought of as a vertical stretch or shrink. So as a result here, I'm going to say that this is really just going to be a times the absolute value of x minus h plus k, where I'm not going to do any thing with the 1 over b's. They're just gone. I don't need them. Is that okay with you guys? Okay. So this is what we're going to be using. So to be able to graph any transformation, all I'm going to need to know is how to graph the original parent function, and then I can just apply that transformation to my parent function. So absolute value, -1 is +1, 0 is 0, 1 is 1, right? Everybody's okay with that graph? So all your absolute values should look like a V. this point here is special. It has a special name. It's called the vertex. That's the tip of the V. In the case of the parent function, it's 0, 0. So for any transformation then, any absolute value graph that we've performed a transformation on, what is the new vertex going to be? So the y-coordinate would be k. What's the x-coordinate going to be? H. So remember, the A, H, and K, what they do, remember A is a vertical stretch or shrink. Is that going to affect the location of the vertex if we're kind of pulling up or squishing down? No. Or it reflects it across the x-axis. Will that affect the location of the vertex? Not when it's at 0, 0, right? Okay. The H and K then shift. H shifts left and right. That'll affect. And the K shifts up and down. That would affect. So just the amount we've shifted left or right is my new x-coordinate. And the amount we shift up and down is our new k-coordinate. Everybody okay there? So that's an important result, but kind of an obvious one after we approached it kind of the way that we did, right? Which is why we spent all that time at the end of last chapter talking about transformations. It's because this is how we're going to approach basically all of the functions that we deal with. We're going to study their parent function, and then we're just going to find some key features from the parent function and transform them to get our new graph. So let's do an example here where we just graph one of these things. So let's say that we want to graph the function y equals -2 times the absolute value of x plus 3 plus 1. So just like we did before in the last chapter, I would start by identifying my values for A, H, and K. What's my value for A? -2. What's my value for H? -3. Remember that the H is always the opposite sign of what it appears. And my value for K is +1. The K is always the same sign as what it appears. Okay. So then I'm going to write my transformation map. The same way that I wrote it before in the last chapter. This is why I said that eventually you won't have to worry about memorizing these things because you're going to do it automatically because you're going to do this so many times in the homework that, boy, it's going to be a waste of time if you don't memorize this and have to keep looking it up over and over and over again, right? Okay. And now I'm going to use just those 3 key points that we graphed to graph the parent function. So there's my graph of g of x. Is everybody okay with that? Very similar to what we did last chapter, right? In fact, remarkably similar. In fact, the whole year when we're graphing is going to feel about the same. Everybody's okay with that? Lovely. Let's talk about the domain and range here, and that'll be the last thing. So the domain and range for something like this. Well, let's go back to the parent function. What's the domain and range for a parent function? The domain would be, I have a left arrow and I have a right arrow, and they're connected. So I have all the axes. Everybody agree with that? My low y coordinate is here, so that's 0. And I know that's included because the vertex is 0, 0. And I have arrows pointing up. Everybody's okay here. So this is the parent function. So for our transformation, can the domain change? If it was all real numbers before, and we're just transforming it, it's still going to remain all real numbers, right? The range is a little bit trickier. What do you suppose it's going to be this time? So it's going to be the y-coordinate of the vertex, which we said was k, to positive infinity, assuming that our v is pointing up still. But remember, we could reflect across the x-axis, so sometimes the v could point down. So we have that. Are we okay there? Okay. So if we go back and wanted to write the domain and range for this previous example that we just did, the domain is always all real numbers for all absolute value functions. That's easy. And the range, well, we're pointing down. So we're going to go from negative infinity up to k. What do you guys think? We did a lot of stuff today, right? Hopefully it felt okay. Was the pace okay? You guys feel like you have a good handle on what we've done so far? I find that students typically